All right, today multiplying a vector by a scalar. Before we even start though, let's make sure we're clear on what a vector and a scalar are. That might be obvious, but just let's be clear. A vector means magnitude, so something with size, and direction. Sort of what we've been talking about all chapter. You can picture arrows. These are directed line segments that we have been building. A scalar is just a number. So we're talking about a 3 or a 5 or a 7 or a 2.9, whatever number you want to think about. Well, it's a nice lesson. Pretty straightforward what we have to accomplish here. So take a look here. For the following vector, find the sum v plus v plus v. So there's v, and if I want v plus v plus v, well, I'll need another v here. And then I'll need another v there. And so I get this vector sum v plus v plus v, all in the same direction. So as you might expect, v plus v plus v, what we're really talking about is 3v. And if you think that's simple, well, it is. This lesson is simple. It's a simple situation. What's going to come later, just to preview what's going to happen, is what happens when we multiply a vector by a vector. And at this point, there's no way of knowing what that could possibly even mean. That's when things are going to get, I won't say difficult. It's not difficult, but it's just a different look at things. So we start off with multiplying a vector by a scalar, and this is pretty straightforward stuff, as you would expect. Next, it says a vector negative 2v would be the same thing, but in the opposite direction. So there's v, I want negative 2v, so I'd need the v's going this way instead. Each one of those is a negative v. Each one of those is a negative v, and so what I get out of that is the vector negative 2v. Very, very nice. So the operation of multiplying a vector by a scalar is called scalar multiplication. How nice is that? It uses the exact words we'd want to. So just to really narrow down the definitions here, let v be a vector and let k be a scalar. Kv is a vector. Let's get my highlighter out. Ooh, orange. Kv is a vector that is k times longer, as long as v. So a couple of things. If k is greater than 0, what we mean by that is if k is positive, then kv will have the same direction as v. If we're multiplying by a positive number, our vector is going to go in the same direction as it did before. We saw that up here with 3v. Positive 3b went in the same direction as v. Now, then, if we go to, if k is less than 0, that means if we get negative k values, then kv will have the opposite direction of v, and that's what we saw in the negative 2v example up here. It went in the opposite direction that v went. And if k equals 0, when we multiply k times v, we get the 0 vector. Which again may seem weird that 0 and 0 vector are sort of different things here, but you'll get used to it. So note the similarities between multiplication in arithmetic and scalar multiplication of vectors. You're going to see a lot of similarities here. This is going to work pretty nice, scalar multiplication. Just a few more visualizations here. For the given vectors, sketch 2a. And so this would be the vector 2a. And so we'd need an a, and then another a. And then that's the vector 2a. Then they want negative 3b. So b is heading right to left there. So to get negative b, we're going to have to go this way. This will be negative 3b that I'm drawing here. A negative b vector, another negative b vector, and then another negative b vector. That's what negative 3b would look like. And finally, half b would be in the same direction as b, but about half as long. A little more careful with my arrows there. There's half b. So sort of works the way you might expect. Important definition here. Two vectors are said to be collinear if they lie on a straight line when arranged tail to tail. Notice if one vector is a scalar multiple of another vector, the two vectors will be collinear. Now you might be thinking parallel here. And it really is a lot like parallel. There's a few more implications here, but really we're talking about the two vectors will be parallel. The only difference here is that the vectors could be right on top of each other and they're still considered to be collinear. So it's got a little bit more to it than parallel, but parallel will do for now. And what about the zero vector? The zero vector, weirdly, is parallel. Sorry, not parallel. Collinear with all vectors. Since 0 times whatever vector will always give the zero vector. So there's always a way to multiply by something and end up with a zero vector. So we consider those all collinear. That's a little different than parallel. Parallel, you sort of have to see them in the same direction. Collinear is more about coefficients and what you're multiplying by than it is really about the geometric side of things. So just a little bit to get used to here that collinear is different. To be honest, that's not really how we use collinear. That's a special case of collinear. So don't let your brain bend too much on that right now. That's not the really important part. The real important part is what happened up here is that collinear, we're really talking about parallel vectors. Another important definition, not particularly difficult, but it's going to have big implications for us later. Scalar multiplication of vectors is often combined with vector addition and subtraction to give linear combinations. So a linear combination of the vectors u and v has the form au plus bv, where a and b are scalars. What I mean by that is lots of times we're going to have a u and a v, and we'll go, oh, we want 3 u's plus 2 v's, or we want 7 u's minus 9 v's, or 15 u's minus 16.4 v's. You know, there's going to be all these different ways to do it, and all these are linear combinations. And why they're called linear is we're not multiplying by other vectors. We're not multiplying by anything strange there. We're just multiplying by numbers out front. So just to get used to that, we'll draw a couple of diagrams here. It says for the given vector a and b, sketch negative 3a plus 1/2 b. So negative 3a would look something like this. There'd be a negative a. There'd be a negative 2a. There'd be a negative 3a. Negative a, negative a, negative a. Plus 1/2 b. So 1/2 b in about this direction here, but only about half as long. There's 1/2 b. So then I'm going to do this in red here, carefully. Not bad for freehand there. Let's try it one more time. Oh, that's a little better. So this is negative 3a plus 1/2 b. And we're drawing these. We try and draw them pretty neat here, but we're not really getting too crazy about drawing them to scale. We're just trying to get the idea of what these things look like. So there's negative 3a plus 1/2 b. So I've taken negative 3a and I've tipped to tail, added on 1/2 a b, and then my resultant vector there is in red, and it's negative 3a plus 1/2 b. This is the type of question you're going to run into, this last example for today, where you have to draw everything out. So I'm going to be a little more careful with my drawing here to really get the idea of what they're getting at here, and I've left lots of space here to do my drawing. Just put that right up the top. Okay, ABCD is a parallelogram. Okay, just give me a second to patch this all together because I'm going to have to insert some stuff here. Shapes. Ooh. Might there be a looky, I got a parallelogram. How exciting. Oh, it wanted it up there. So let's get rid of that for a second. I know how to fix this. Get rid of that keyboard. And then back to here. Get rid of that keyboard, back to here. Okay, and we want to just tap here. Get rid of the keyboard. And then when I insert my parallelogram, it'll be about where I want it to be this time. I wasn't expecting to have that available. So let's just grab that. Just move it up a little bit. And, oh, beautiful. That's going to be perfect. All right, so let me just label the corners here. It says ABCD is a parallelogram. So let's get back to my black pen here. And here we go. A, B, C, D. Now, if you haven't seen a lot of these type of setups before, I just need to tell you that this ABCD does sort of matter in that ABCD tells you the order of the vertices. I could have gone counterclockwise. That's fine. That wouldn't have changed anything about the whole situation. It just would have flipped the situation. But I can't go, I had to go A, B, C, D around the outside there. I couldn't go A, C, B, D. You know, like, so the way the letters are set up in the description of the parallelogram does tell you which way to go around. So ABCD is a parallelogram with P and Q. Okay, let's talk about P is the midpoint of AB. So here's P right there, and that's a midpoint. So I'm just going to draw these little lines on there to indicate that P is halfway between A and B. And then Q is the midpoint of DA, so that's right down here. Right about there, that's Q. And I'll just add some lines in there to say, okay, that is the midpoint of DA. And U is BP. So U is the vector. Okay, I'm going to switch colors here so you see what's happening. There's a little more than meets the eye to this question. There's the vector U in red, and it says it goes from B to P. So I'm just going to make this just a little bigger. I hope that's big enough so you can see what's happening here. There's U right there. It goes from B to P. Next, V is AQ. And I'm going to use a different color again for V so we can really see where these things are. There's the vector V, and it goes from A to Q. So there's the vector V there. A couple of things got messed up while I was doing that, so I want to fix them up here. They don't seem like a big deal, but they are with the way this question is going to play out. I just need that on there, and I need those like that. Okay, so that's pretty good, I think. That's a pretty good setup of the drawing. So that's the type of question you'll run into sometimes where you can do this whole drawing setup before you do the question. And actually, I think as it plays out, the question is not all that hard, but the setup is a little bit awkward. So let's do A up here, and they want to know, express the following in terms of U and V. So they want the vector CD, which I'm going to highlight on here. There's the vector we want to talk about here, CD, in this particular question. CD, though, they want it in terms of U and V. So how many U's and how many V's make up CD? And I'll let you stare at the diagram for a second without having to pause the video and see what you, where you see how I can make up U's and V's for CD. The important part here is this is a parallelogram. So CD and BA head in the exact same direction, which means if I want CD, I need a U and then another U. So CD is equal to 2 U's. Now I know you're like, U's way over on the other side. That doesn't matter. U can be thought of as over here on this side as well. Let me draw it on there real quick. There's a U as well, right there. So the actual locations of the vectors in space doesn't matter. It matters what direction they go and what size they are. I want to get rid of that because I don't want my diagram to get too crazy here. All right, let's move on to B. B is BD. So BD, we want to get all the way around this parallelogram. So we want to get, let's see if it's going to let me just poke that. Oh, it does. Oh, that's nice. Okay, so now I want BD, I want to get right from here to here, but I want that made up of U's and V's. So just stare at that for a second and see how you can use U's and V's to do what BD did. So if you see there, what you can do is go along the outside here and then along the outside there, and that will give you the BD you need. And again, in the interest of not letting my diagram get too messy, I'm going to get rid of those little highlighters I put on there. And so I hope you see now that BD will be equal to 2 U's plus 2 V's. Now C. I'm hoping again it's going to let me pluck this stuff off. Oh, that's nice the way that does that. Okay, next. PD. So they want from the point P here over to D this time. Hopefully you're sort of used to this by now. If not, maybe rewind the video and watch the first two. So if I want to do just P, D, I'm going to need only one U and then two V's. You see, P being the midpoint of there was a really big deal because it allowed me to go, oh, two U's goes all the way from B to A. I only need one U to go from P to A. Okay, so let me just clean up my diagram a little bit. What do I want to get rid of here? Get rid of that and that. Okay, good. And the last question here, D, is they want AC in terms of U and V. So AC goes from here to here. And there's two ways I could handle this situation, actually. I could go this way around, and I would get two V's. Now, careful here. If I want to go this way, I can't use U's. I got to use negative U's in the opposite direction of U's. So I'd have two V's minus two U's. Or maybe you're thinking 2V plus negative 2U. And that would be right too, but that would be the same as subtract 2U. There's another choice here, as I could have gone this way around. And check out what happens here. I would start with negative 2U's. And then I'd need two V's. But take a look at those two different answers. And I hope your algebra experience says, well, those two things are the same things. And it's so nice that vector algebra sort of works that way, is that it works a lot like regular algebra. So there's no really big deal here about changing back and forth, putting things in front or behind. And so you're going to get used to that. Last little point here, if U and V are non-zero, non-collinear vectors, and it won't become clear why those rules are in place, maybe for a little while, but if we have two vectors that neither of them is zero, and they're not collinear, they're not parallel, then any vector OP in the plane. So this claims that if there's a vector OP in the plane, in the same plane as U and V, that you can always come up with these numbers, M and N. There'll be two different numbers, and we don't know what they are yet, but there'll always be a way to make every OP, every vector in the plane, as some combination of U and V. So just to give you a flavor of what I mean by that is, say someone's got this OP there, like this, and there's some OP there, and you've got some vectors, so you got a U like this, some V like that. I don't know exactly. It doesn't really matter. What we're saying is we can make up this OP with a certain number of U's, trying to make it plausible here, and then a certain number of V's. There's always going to be a way to do that. How many U's and V's? Well, okay, that'll be some algebra. We got to figure it out. But there's always a way to go OP equals some number of U's and then some number of V's. So maybe it'll be like 6 U's and 2 V's, or 3.2 U's and 4.1 V's, or, it really depends on the situation. So I've drawn an easy looking one, but they can get weird looking so that you might get negative 2 U's plus 4.1 V's. We don't know what these numbers are going to be until we get some more evidence. All this is saying is there will be some numbers that will make this work out. As long as the two vectors are not zero, and as long as they're not parallel, that this will work out. More of that in later lessons. Just let that bounce around your brain a little bit. Maybe look that over at the end of every set of homework for a little while and just remind yourself this is coming. But more of that later. Okay, so that's the end of multiplying a vector by a scalar. Take a look at that homework, knock it all down. I encourage you, do as much homework as you can, because the little pieces of this are going to start to build up. Even if it seems so easy, it's really important to get all these basics down pat, because things are going to ramp up as we go along here.